Hello dear students, let's start with one important topic, that is design of isolated footing. Many times asked in engineering service exams, even state PCS also, and gate exam also. Some concepts will be useful from this, and of course for your semester exam also it will be useful. So this topic is very useful, and many students get confused, but now just I have simplified it for you. So before starting the design of isolated footing, let us begin with some basic terms. Okay, so what is the difference between footing and foundation? Footing versus foundation. So many are getting confused between footing and foundation. So footing is basically a structural element, we can say, which is used for transferring the load from either building or from column. Okay, there may be, this is your actual footing, you can see this is your footing. Okay, so this portion, this I am drawing in 3 dimension. See, so this is your actual footing, this part is your footing. It is a structural element which is used for transferring the load from building or from either from column, or there may be some wall also, like this in longitudinal direction. So this is your footing, and the whole structure means including the surrounding soil. This is, there may be some soil or earth, so whole structure, it is termed as foundation. So basically footing is a part of foundation, and here we are supposed to provide safety against sliding. Okay, safety against 2 things. One is sliding and another thing is overturning. Always be careful while designing this isolated footing. You have to be careful for sliding as well as overturning. Then only we can say that the loads are properly transmitted to the foundation. Okay, now isolated footing, the name itself is saying that it is isolated. Okay, isolated means it is alone. It is not combined with any other. So here another thing which you should know is the difference between deep foundation and shallow foundation. So there is not much difference, there is just a technical thing you have to remember. Suppose in deep foundation your depth is greater than the width of the foundation. This thing was given by one soil scientist named Tarzaghi. Okay, so whenever depth is greater than the width of the footing, then it is deep, and a foundation is shallow if its depth is equal to or less than its width. So depth is less than or equal to B, then we can say it is shallow foundation. So there are many examples of shallow foundation, like spread footing. So spread footing is also one type of isolated footing only. So there may be strap footing, even combined footing. These are all examples of shallow foundation. We can say mat or raft footing. So and for deep foundation there are another examples. The most common is, we all know, that is pile foundation, or pier, P-I-E-R, pier, even well foundation. Okay, so there are many examples of deep foundation as well as shallow foundation, but the basic criteria which you should remember is if D is greater than B. Okay, D means, here again you will ask what is capital D and what is, so see, you can see here, this is your this is your width of footing, that is capital B, and this is your depth. Okay, so when D is greater than B, it is termed as deep foundation, and shallow foundation if its depth is equal to or less than the width. So depth is less than or equal to width, so obviously it will be shallow foundation. So this criteria was given by Terzaghi. Now for regarding this different type of footings and there are certain criterias for at which place or in under certain circumstances you have to use a particular type of footing. Okay, so that I will be covering in next video, because here I will be mainly concentrating on what design of isolated footing, right? So let's start design of isolated footing without wasting any time. So here especially for rectangular footing, okay, rectangular means it will be rectangular in shape when seen from the top. Okay, means in plan basically it will be rectangle. So like this, see, this is your isolated footing. Okay, this is your ground level, this is your depth, actual depth of footing, and this is your width of footing, that is capital B. Okay, now while designing isolated footing, certain data or some given values will be there, you should know prior to designing. So first thing which they will be giving to you is load. So load of column or load on the column which is to be transmitted. So load represented by P, the capital P. Second thing which they will be giving to you, that is bearing capacity of soil. Bearing capacity is the basically it is supporting power of the soil, or we can say shear strength, its strength to support. So bearing capacity of soil generally denoted by small qu. Third, they will be giving size of column, or we can say dimension of column or dimensions. So dimension of column will be fixed. Okay, see, you are designing the isolated footing, so we don't know the actual size of footing, but the size of column will be given to you. Then they will also give you grade of concrete and grade of steel also. Okay, so grade of concrete, it may be whatever, M20, M30 grade of concrete. M means mix and 20 is your 20 Newton per mm square. So it's compressive strength, basically it is compressive strength. Okay, so these things you all know what is grade of concrete. So whatever the value of FCK will be given, you can use, it is characteristic strength. Then grade of steel also, you know, it may be either Fe 250, Fe 415. Okay, so whether it is mild steel or HYSD steel, basically you have to know the values and you have to use it according to the given data. Okay, now these are the data which we are supposed to use in the while designing. Now working approach means which steps needs to be followed. So first is your foundation size. That we need to find out foundation size, what we will be providing. Second step will be See, I will be explaining each and every step in detail, but first we will write down the working approach. So first is foundation size, second is check for bending moment, third is to find out depth required. It is very, very important. So then next step is check for single shear or one-way shear. It is also known as one-way shear. Then next step is check for two-way shear. It is also known as punching shear. Then we have to find out the area of steel for longer span. And last step is area of steel for shorter span. Longer span and shorter span means we know it is a rectangle. In plan it is rectangle. So suppose this is your L, so this is longer span. So what steel is provided in longer span, that we have to find out. And this is your width B. So this is along the shorter span. Okay, so these are the 7 steps which we need to follow. Okay, one by one we will see these steps. Okay, so first step is foundation size. Foundation size means again it is the dimension. So here let me draw. See, for your purpose, for understanding purpose, I am drawing it again and again so that you can visualize. This is your actual width B and this is your actual depth D. But if you see it in plan, it will be like this. Okay. This is your column. Okay, now load from column it is given as P. Okay, it is given as P. Now see, this is your again B and this I can say L. One is long, another is short. My drawing is not that good, so again I will draw, don't worry. So load from column is your capital P. Now we have to add 10% weight of foundation. I have explained to you what is the difference between column and what is difference between footing and foundation. So add 10% weight. Why 10% weight? Basically that is weight of foundation. 10% weight means 10 by 100 of P. So it is basically 0.1 P. This is weight of foundation. So what will be the total load? Total load PT will be P plus 0.1 P, that is 1.1 P. Now remember one thing, here the load from column, the actual load, I am not taking any partial factor of safety. which actually in limit state of limit state method I am supposed to take, but here in designing column there is no need to take any factored load, or we are not multiplying it with factor of safety right now. Okay, so here I am directly writing capital P. So capital P is the load from column. Okay, and just I am adding 10%, that is weight of foundation, because that also ultimately it will be transferred to this part, this, okay, at the bottom of this foundation. So total load PT will be 1.1 P. So remember here P is unfactored. Let me write, for LSM we are using unfactored load for calculation of area. Now simple formula we know. What is stress? Stress is basically force upon area, right? So whenever we want to find out area, here we will be finding out the area of footing. So what is the area of footing? Area of footing A is equal to, it will be force upon stress. So basically it is total load divided by stress. Stress is, what is stress? That is bearing capacity, which will be given to you from geotechnical engineering lab. They will be testing the soil and they will be giving you the bearing capacity of soil. So area of footing will be total load, that is represented by PT, right? And bearing capacity of soil, that is represented by small QU. Very, very simple. Now see, once we have got the area of footing, so we need to find out the dimensions. So how we will find? We know the formula, that is area is basically L into B. This is your footing, so area is equal to L into B. So appropriate L and B we have to choose. Okay, here we have to choose L and B according to our, because we will be ultimately we will be designing the isolated footing. So value of L and B we have to choose, but ultimately we have to satisfy this equation, A is equal to L into B. Okay, so area should not be more, as well as area provided should not be less also. So here after selecting or after choosing L and B, then we should know that is net soil pressure. Again see, net soil pressure, net means it is not gross, it is net, because here we are having two things. We are having actual load from the column and we are having the self weight of column also. So W is equal to, net soil pressure is equal to load from column without self weight divided by area provided. Okay, so net soil pressure is load from column without self weight. Now net soil pressure over foundation. So here it will be again represented by small w. Okay, here see, we have seen that your net soil pressure was load from column without self weight, divided by area provided. Area provided we know, but if I am talking about net soil pressure over foundation, then it will be the difference between the total force and your weight of foundation divided by A. So basically it will be P upon A only. Okay, so now we are using limit state method. So for limit state method, what we will be doing here, we will be taking the factor of safety. So net soil pressure will be represented by not W, it will be represented by WU. Okay, and it will be the P by A factor will be multiplied by 1.5. Remember this thing. You should not directly multiply 1.5 in the beginning. We are supposed to multiply 1.5 at this stage, that is net soil pressure. So net soil pressure will be 1.5 P by A. See, again I am drawing this figure again and again. See, this is your let me draw in 3 dimension like this. Okay, so the soil beneath, this is UDL. Here also there will be some load. Okay, so here the force acting beneath the soil, okay, so that is force or we can say stress. Stress is force upon area. So which force? It will be the total force, PT upon A. Okay, are you getting it? It is PT upon A because it is total force. Force coming from the column as well as force of the foundation. That's why it is PT upon A. But the some force will be here, from top to bottom. So this will be PF upon A. See, the area is common, so area is same for both, but PF is your the weight of foundation, that we know. So net will be PT minus PF divided by A. So denominator will be capital P and numerator will be capital P, denominator will be A. So next step will be your check for bending moment. Check for bending moment. Now here again I am drawing the plan. See, this is the plan. This is my length L, this is my width B. Now L and B I have fixed. Okay, so now I can't change L and B. Now next step, which and they have given me the size of the column also. Okay, so inside it is column. So column dimensions are small a and small b. Okay, so don't get confused with capital B and small b. Small b is the dimension of the column and capital B is the dimension of the foundation, actual foundation. So capital L, capital B. Now here one thing which you should remember is you have to take, what you have to take? You have to take the critical section. That you have to remember. Okay, and where you have to take this critical section? Critical section for bending moment. Okay, for bending moment at the face of column. Face of column, it means the boundary of column. So what is the boundary of column? Where is the boundary of column? This is your boundary of column. See, this is your boundary of column. Okay, let me change the color. So suppose face of the column, I am taking the critical section. Now I have two directions, one is XX direction and another is YY direction. So X axis is horizontal, Y is vertical. So your face of the column, this is my face of the column. See, this is my face of the column. I can take the below side also, this side also I can take, but one side I have to take. So I am taking this as x1, right? Same way face of the column in vertical direction, this will be my y1 y1. Okay, so this is the critical section when I am checking for bending moment. Now I have to take 1 meter strip for in both the direction. Suppose this is my 1 meter strip. This is my 1 meter strip I am taking, and in this direction, see, this I can take anywhere. I can take above or below. So basically it should be 1 meter only, and this strip I am taking on the one side of x1 and another side on a particular side of y1. Okay, and I have to take the moment. Now we know what is moment. Moment is basically force into distance. Force into distance is moment, right? Force into distance. So here what I will be doing, I will be first of all taking the force here. It is the weight of this strip, weight of this particular strip, red strip. This is my, I have to take this weight, and I have to take the moment along x1, and for this strip, this is, let me write, this is strip number 1 and this is strip number 2. So for strip number 1, I will be taking the weight of this strip and I will be taking the moment along x1, and this for strip number 2, I will be taking the moment weight of the strip 2 and I will be taking the moment along y1. So basically I have to find out the distance CG will be exactly here half. Okay, suppose I am taking here again, so CG will be here. Same way for 2, the CG will be at the center. Okay, let me draw it again on different page so that you can understand better. Okay, see, just concentrate over here, it is very, very important. Okay, this is your A, this is your B, this is your capital L, this is your capital B, right? So when I am taking this, again I have to change the color. Okay, so I am using black color now. Okay, so this is my x1, and this is my y1, and this is your strip. This is 1 meter. So if this is my 1 meter, same way here also, this is my width is 1 meter. So what is this distance? This much distance, because width is 1 meter. The strip width of this strip is 1 meter. So what is the length of this strip? Can I find out the length of this strip? So to find out length of this strip, I have to take the center line. See, this is my center line. So center line, this total will be half, that is b/2. So when I am subtracting this portion, small b/2, so this distance, let me write it as OY1. OY1 is the width of this strip. This is my OY1, this portion. Okay, so OY1 is equal to capital B/2 minus small b/2. We have to subtract this distance also, because this column, this is your column, this black portion, totally I am totally making it black. So this is my column. Okay, so half of the distance I have to subtract, because this half is capital B/2 minus this half, this much, this is my small b/2. So this distance is OY1. So OY1 is equal to capital B/2 minus b/2, that is denominator is same, so b minus b by 2, right? Now I have to take maximum bending moment about which axis? About x1. So for bending moment, we know we have to multiply force and distance. Okay, so force is basically the weight of this strip. So what is the weight of this strip? So weight is small w is your net pressure. We know net soil pressure, multiply by the area. So area of strip is 1 meter, 1 multiply by this distance b minus b by 2. So this is the area of the area, and this is weight. So this combined term, this is your force, because this weight small w is basically, what is small w? Small w we know that is p by a. So, and this is also a. This portion is area of strip. This portion is your area of strip. See, don't get confused in this derivation. It is very important. This 1 into b minus b by 2 is your area of strip. Okay, and w is your p by a. So basically this portion, this represents the force, multiply by the distance. Now distance we have to take from the centroid to x1. Okay, so centroid, this is half of OY1. So what is b OY1? OY1 is b minus b by 2 divided by 2. So it will be b minus b divided by 2 and again divided by 2. It will be 4. Okay, so your maximum bending moment will be, just multiply w b minus b whole square, because it 2 times 2 into 4, that is 8. Okay, I hope you are getting it. So force, and this is your distance. This particular is CG distance from CG of strip to x1. Okay, distance from CG of strip is your center, to the x1. See, same way we can find out this distance. This is your OX1. So if I want to find out moment about y1, so I need to find out the OX1. What is OX1? OX1 is basically the length of this strip. What is width of strip? Width of strip we have taken 1 meter. So length of strip I have to find out. So it will be this half, L by 2. This is your L by 2 minus, now it will be half of A. So it is A by 2. So it will be L minus A by 2. So your maximum bending moment about y1, again we have to take the force into distance. So the weight of the strip will be W into the area of strip is 1 into L minus A by 2 multiply by the CG distance from to y1. So it is L minus A divided by 2 and again divided by 2. So it is L minus A by 4, because it is half here, the CG is here. Okay, so this is from this portion you have to multiply. So you have to take the moment. So it will be W L minus A whole square divided by 8. Okay, and remember one thing here, you have to always for limit state method, our WU will be multiplied by 1.5. Okay, so don't forget to multiply by 1.5 the W value. Okay, so this is your step number 2. Now we have got the maximum bending moment about x1 as well as maximum bending moment about y1. Okay, so next step is depth required. So third step is to find out depth required. So here remember one formula, D is equal to under root mu max divided by QB. Okay, so this is very important formula, so that generally we can directly find out the depth required. So it is under root mu max upon QB. So per 1000 mm also, many times per meter width we can find out the depth, but for LSM we are directly using this formula. For limit state method we are using this formula. So this is our step number 3. Then for step number 4, fourth step, it is check for single shear, that is one way shear. Okay, so one way shear. Now again I am drawing the same figure. See, this is my L, this is my width B, and this is the dimension of column, that is A and B. Okay, now for checking for single shear, one way shear, again we have to take what we have to take. We have to take critical section. Again I have to take critical section. Now another question, where we have to take the critical section. So again remember, critical section for one way at D distance, small d distance from the face of column, from the face of column, at a small d distance from the face of column. So what is small d? Small d is basically the effective depth. Okay, so here this is my face of the column. Again I am changing the color. Small d is your effective depth. So your critical section I am not taking like previously I took at the face of the section for bending moment, but here from the face of section I have to go a distance. How much distance I have to go? Small d. So my critical section will be somewhere over here. Okay, you can see here, this is my face of the column. So this is distance d, small d. Okay, so here this will be my x2. Okay, again for vertical direction, this is my face of the column. So I will be taking my critical section somewhere over here. This is my y2. So from face of the column I have to go slightly this side. So that is how much? D distance I have to take my critical section. So for single shear my critical section will be at a distance d from the face of the column. Okay, now I will be taking the small strip. Okay, so small strip will be starting from here. You can see this is my strip and this is 1 meter width. Again here also small strip will be this one. So this is my 1 meter. So I know the width of the strip, it is 1 meter, but I don't know the length of the strip. Okay, so again I will be finding out the overhang, or we can say length of the strip. So let me write it like this is your OY, overhang. So here I am supposed to find out the shear at x2 x2. I will be basically finding out two shears in xx direction and in y2 y2 direction and x2 x2 direction. So shear at x2 x2, for finding this, my overhang, what is my overhang? Overhang will be OY. Overhang I am representing OY. So what is this OY? How much distance it will be? So it will be, again I am dividing it into half. So it will be this b by 2 minus this b also I will be taking half, small, minus b by 2 minus d. Can I write? Because d also I have to subtract from here. Okay, so it will be basically b minus b by 2 minus d. Okay, let me write it down. Okay, otherwise it is getting congested. So b minus b by 2 minus d, that is OY. So now what will be the shear force? Shear force Vx is equal to, see here I am not supposed to find out moment, I am just I am finding out the shear force. So basically it will be area of this strip multiplied by weight. So weight W is, that is small w, and what is area of this strip? So width is 1 and the length is, that is OY, multiplied by OY. What is OY? So W into this thing, let me write capital B minus B by 2 minus D. So this is your shear force Vx. Same way we have to find out shear force at y2 y2. So what will be the overhang? Let me write as OX. So OX, so it will be, now here I have to consider this half portion. This is your L by 2, half is L by 2. So L by 2 minus A by 2 minus D. So it will be L minus A by 2 minus D. Is it clear? Okay, so next thing which we have to find out is your shear force. So what will be the shear force? Shear force will be the force acting on this strip, right? So that is weight multiplied by the area of the strip. So shear force at y2 y2 Vy is equal to your weight W multiplied by area of this strip is 1 multiplied by OX. We have represented it as OX, right? So into OX, so it will be W multiplied by 1 into OX. What was OX? It was L minus A by 2 minus D. Okay, same thing we have to write down here. W multiplied by L minus A by 2 minus D. So now we are having two values. One is Vx and another Vy. Okay, from both we have to take the maximum shear force. So we will get any of the force, may be maximum Vx or Vy. And next we should know what is nominal shear stress. Tau V is equal to Vmax upon Bd. It should be less than tau C. This condition usually gets satisfied. Okay, so don't worry. Even if you see this formula is given in IES 456, so tau C is your permissible design. Tau C is permissible design shear strength. Of concrete. Basically it is also expressed in Newton per mm square. So footings are generally safe in shear. So shear reinforcement, in while designing beam we are providing stirrups. Okay, so no need of such type of shear reinforcement while designing footing. Okay, next which will step is your check for two-way shear, or it is known as punching shear. Punching shear means one type of puncher. Okay, generally in our vehicles we get puncher. So puncher means piercing, one type of piercing going through. Okay, so here also let me draw the figure. See, this is my L, this is my B, and this is my dimensions of columns A and B. Okay, now here also I am supposed to take what? Critical section. The next question is where I have to take the critical section, where I am supposed to take the critical section. So here the critical section, at which place we have to take, that is very important. So critical section for punching shear, which is also called as two-way shear, it is at a distance of d/2 from the face of column. So again, face of column means this boundary. Again, this is the boundary, this is the face of the column. So from here we have to take a distance d/2. So suppose this distance here, so from here it is d/2, small d/2. Okay, again, so this is my critical section. Again, let me change the color so that this is my critical section. This is from face of column, this is small d/2. Again, critical section from this face, here also there will be critical section. So here also this is d/2. This is face of column. So again from here, this is this distance, this is my d/2. Again here this is d/2. It is getting very much congested. Okay, I hope you are understanding. So again, let me draw properly. This is L, this is B, A and B. Okay, so you can see again here d/2 on all these sides. So how the figure will look? The another figure means same figure, if I am modifying it, if I am putting d/2 on all the sides, it will look somewhat like this. Okay, so this dimension will become how much? d/2 on both the sides. So it will become a plus d. A plus D. Okay, A plus, let me rub this. It will be A plus D. Okay, and what will be this dimension? This dimension, it will be B plus D, because D by 2 is on both the sides. So this is your, see, this is my shaded area. Okay, now when I am taking critical section, this critical section I am supposed to take D by 2 from face of column. Remember this thing, that I am taking this critical section D by 2 from face of column when I am considering two-way shear. If it was the case for one-way shear, it would have been small d, okay, from face of column. And if it is the case of bending moment, then I have to take exactly at the face of column. Okay, so in three cases we have to take the critical section, but the distance is different. If it is bending moment, then we have to take exactly at the face of column. If it is one-way shear, we have to take at a distance small d, and if it is a case of two-way shear, I have to take at a distance of d by 2. Now here the twist is, what is the twist? See, you have to imagine one thing, that whenever the for two-way shear is taking place, it is basically punching. Punching means it is making puncture. Puncture means it is trying to make a hole. So the column will go inside deep, and your footing, okay, this is your footing, suppose this is your footing, okay, just imagine in 3 dimension. So it will go inside like this, okay, it will make a hole here, there will be a hole, okay, hole like this, and the whole column will go inside, it will puncture the footing. Okay, so when you are considering two-way shear, or when you are considering this punching shear, the area or the cross your critical section which you have taken, you have to take the whole area or whole perimeter. Basically the perimeter here will be this perimeter. I am talking about this perimeter. This is your A plus D, this is your B plus D. So the perimeter will be A plus D plus B plus D, again A plus D, and again this will be B plus D. Alright, so this is your perimeter, and the column will be going deep inside this hole. Okay, so here this depth small d, okay, here that depth also you have to consider. Okay, so when we have to see the punching shear, we have to find out the punching shear, we have to check the shear force which is resisted by the area, cross section area. So here I will be taking this perimeter A plus D, B plus D, plus A plus D, plus B plus D. Okay, so what will be my net punching force? Net punching, what will be my net punching force? That is P net. Net punching force will be the actual force or actual load, that is P, which is coming from top, that is from column, minus this area and weight. So W into the area is L into B. So here L is A plus D and this is B plus D. So basically this is your area. So force upon areas, we know small w, What was small w? Small w was, it was pt minus pf by a. So basically it was p by a only. Okay, small w was p by a. So here p net is equal to capital P minus w into a plus d into b plus d. This is a small derivation, but if you know the derivation, you can easily calculate or easily design the all the values of isolated footing. So this is net punching force. This is a net punching force. Punching force when there will be a puncture, there will be hole inside the footing. The whole column will go inside, right? So after finding out the net punching force, the punching shear stress, because force will obviously develop some shear stress also. So punching shear stress will be developed. So basically what is stress? Stress is force upon area. So here the force is net punching force divided by cross section area. Now which cross section area? Now don't consider this cross section area a plus d into b plus d. Okay, cross section area of resisting section. See, many times students are making mistake that resisting cross section area, this cross section area you should not write a plus d multiply by b plus d. Okay, this is wrong. Don't take this cross section area. This is not the cross section area. The cross section area is this one, the inside cross section area. Okay, so let me draw it again. So please don't take this cross section area. It is wrong. See, so this is dotted line. Okay, so this is your a plus d and this is your b plus d. Now when this resisting cross section area means this one, this perimeter multiply by the small d. Small d is your like this. In 3 dimension you can see this like this. This is one hole. Inside this hole the column is piercing. So this is my small d will be this. This is my small d. This is my small d. Okay, you have to just imagine in 3 dimension that this is my hole. Okay, in which this column is piercing. So this, in this column, in this portion the whole column will be piercing. So what will be the cross section area, resisting cross section area? So I have to add all these sides multiply by this. So this is I am changing the color so that, so which area I am supposed to find out? I am supposed to find out this area. Okay, this shaded area, red color area. Okay, this area. Okay, this area I am supposed to find out. So the depth d, that is constant. Okay, so suppose this portion, so that is b plus d. So b plus d multiply by d, right? So same way it is on opposite wall, opposite side also it is there. So I am multiplying 2 times. Okay, plus same way the d multiply by a plus d, and there is 2 walls. Okay, so again I am multiplying by 2. Okay, so what I am taking? I am taking 2d common. So 2d I am taking common. So it will be A plus D plus B plus D. Okay, so this is your actual resisting area. Okay, so please don't make mistake by A plus multiplying directly A plus D into B plus D. Resisting area is your this portion. Okay, you have to just imagine this thing. Once you start imagining, it is very easy. So now I have found out the resisting section. So that is resisting area, that is 2D multiplied by A plus D plus B plus D. So again I will write the formula. Punching shear stress tau Vp, it will be, what is net punching force? That is, we already found out, P minus W A plus D into B plus D. See this formula, direct formula, if you are able to remember, actually you should be able to remember, because direct questions are coming in GATE exam, and you will directly be able to find out the answer. So P minus W A plus D into B plus D, this is your net punching force, and divided by area. Area is resisting area, that is 2D A plus D plus B plus D. Okay, so this formula, please memorize this formula. I think my handwriting are not good. Again I am writing this formula. Tau Vp is equal to P minus W A plus D into B plus D. If possible, you can pause the video and again you can write or make notes. Okay, just wait. Okay, it is 2D A plus D plus B plus D. Note down this formula, and you will be able to find out the punching shear stress. Okay, and again this punching shear stress should be less than the permissible punching shear stress. Again for this also same way, this should be less than, always should be less than what? Permissible punching shear stress. Should be less than permissible punching shear stress. Now what is permissible punching shear stress? What is permissible punching shear stress? For that you can refer the IES code for limit state method. The value given or formula given is tau Cp is equal to Ks multiplied by 0.25 under root FCK. FCK is your characteristic strength, whatever M20, M30 you have to take, so that will be your characteristic strength or grade of concrete. And what is Ks? Ks is some value, I am writing down Ks. Okay, on next page I will write Ks. Ks is equal to 0.5 plus beta C it should not be greater than 1. Okay, remember this thing. Now what is beta C? Again it is dimension of short dimension of column, short side or short dimension of column, not of footing. Okay, it is short dimension of column divided by long dimension In our case it was A and B. Okay, so either it will be A divided by B or B divided by A. Whatever is greater, you have to take it in denominator. Okay, so beta C is short dimension of column divided by long dimension of column. Now next step, which is sixth, that is we have to find out area of steel. Sixth and seventh step are same, because almost same, because we are supposed to find out area of steel here for longer span. What do you mean by longer span? Longer span means along the length L, or we can say parallel to the length, parallel to L, right? So again, let me draw the figure so you can understand. This is my L, this is my B. So the steel which I am supposed to place in this direction, this is along the length. Okay, so it is parallel to the direction of L. So this steel basically, let me write the formula. This formula you have to memorize. Okay, there is no other option. MUY divided by 0.87 FY small d minus 0.42 XU. Very easy formula. Okay, XU is the depth of neutral axis, small d is effective depth, 0.87 FY. FY is your whether it is Fe250 character grade of steel. Basically it is grade of steel. It is either it is Fe250, 415, whatever. So that is Fy. So AST you can find out by using this formula, MUY divided by 0.87 Fy into D minus 0.42 XU. Once you are able to find out the AST, then this reinforcement you have to, how you will place this reinforcement? You will be placing this reinforcement along the length. Okay, along the length, distributed over entire width. Along the entire width. So now we have seen this AST which we have calculated, it is calculated for 1 meter width. I told you that B is equal to 1000 mm. Okay, so for 1 meter width I have calculated this AST. So for suppose for B meter width, what will be my AST? For B meter, my AST will be, or total area, let me write on different page, another page. For B meter, total area of steel will be B into AST. Okay, so which this total area of steel, again it is along the length. Okay, so it is just one part of steel, that is along the length or parallel to the length, along the length or parallel to length, that is B multiplied by AST, because whatever AST we have found out, that is for per meter width, but the actual value will not be 1 meter width, the actual value may be another. So for B meter you have to multiply B with AST, so you will get the total area of steel along the length. Okay, same way, step number 7, that is last step, that is area of steel for shorter span Shorter span means along the width, or parallel to width, okay. See, this is my L, this is my B. So now I will be placing my steel like this, okay. So along the width, here also for 1 meter your formula will remain same, only thing it will be AST will be MUX. Here you have to consider MUX. Earlier we took MUY. So here MUX divided by 0.87 FY into D minus 0.42 XU. This is the standard formula which you have to remember, okay. Same way, this is for, this formula is valid for 1 meter, okay, for 1 meter. So for L meters, the same formula will be total area of steel is equal to L multiplied by AST. So total area of steel, which is along the width, again along the width, okay. So we have to find out two areas. One is along the length, that is along the length steel, along the length and along the width, okay. So these were the 7 steps. I hope you are understanding, okay. Thank you very much.